Yes, this seems to work. Great. I'm learning something new every day, and now I really managed to start on time and see that you can see the presentation. So hello everybody, and welcome to today's live session. This is the fourth of a series for this week, Geology for the Future. Today's topic is water. Feel free to invite your friends or colleagues just by tagging them, for example, in the comments. And I'm also glad if you share where you are watching from, and if you are a geologist or a geology student or have just a general interest in this topic. My name is Sonja Philipp, and I am from Germany. I'm adjunct professor at the University of Göttingen. It's just in the center of Germany. Adjunct professor means that I'm teaching and guiding students, but I don't have a formal position yet. So I earn my living with my own one-woman company that is called Geophil. There I do some consulting in the geothermal industry mainly. So everything related to fracturing and related fluid flow is my expertise. And I also teach these topics. And I also do some excursions and some teaching for the general public that is just interested in geology. So my excursions go mainly to German areas, but I also do excursions to Iceland, a country that I very much. And in fact, my PhD I did in Norway at the University of Bergen. That was also related to fracture propagation in layered rocks. And since then, I added not only layered rocks, but all kinds of rocks, and also it's more related to geothermal energy today than it was during my PhD. That was funded by a petroleum company, but was focusing really on joints and mineral veins in limestones and marls and some mud rocks. Okay, this about me. So I check now where you are watching from before we start, or if I have any other comments. I see that Victor is watching, and Alice says hello, and Said says hello. So I see this seems to work, that you can really see me and hear me. If you'd like to leave a comment really on where you are watching from or what is your profession, we'll look at this again. Okay, there's Cindy from Florida. Nice to meet you, Cindy. I see that there are 35 people watching live at the moment. In case you watch the replay, of course, I hope you can enjoy this lecture too. A general point here, you may always leave your questions in the comments. And in case I don't see them during the live, or you watch the replay and write them afterwards, I will try to reply to your questions and comments later on. We will not meet in Zoom today. I give this presentation using Zoom because then I can share my screen and you can see me at the same time. But we will not have a Zoom discussion live today. We will rather have a kind of Q&A session next week. We will post the date and time, of course, later on. Yeah, there are many people saying hello now. There is Gayla from Bolivia. Hello, and Emmanuel says hello. Telly says hello. Gabriele from Palermo in Italy says hello. Juan says good morning from Colombia. Yeah, good morning to you. Here in Germany, we have, of course, afternoon, and for some people, it's already evening, but that is so great that we can meet via this medium on the entire Earth, in fact. Well, for some people, it's night, but it's so great. I like this very much. Fausto from Argentina says hello. Great, we are 50 people watching now. So then I think I can start with the topic really. The topic today is geology for the future. water. Yes, I wanted to add one more thing. In fact, there were some people asking about the presentation some days ago. This presentation, I can do this live on the internet, of course, but for copyright reasons, I cannot provide the slides. So because I use a lot of material from books or from internet resources, I always, or at least if I remember where I took it from, I give the source and the URL that you can check these references. And if you want to know more about this, you can always ask me later on. But sorry, I cannot give out these because then I would have problems here with the copyright, because these most of these illustrations were not made by me. And so for that reason, I will not send you any PDF file or what of these slides. I hope you understand that you can use the references, of course, and find these illustrations yourself. And if you need any more information, feel free to ask me. Okay, let's start with the topic then. Water is, of course, also a very important topic where geologists contribute. And in the future of mankind, of course, the water problems may even increase. There are many places on Earth where there is too little clean drinking water available, and these problems will increase with the increasing number of people and increasing standard of living, hopefully, of course. So this might be a greater problem in the future. Okay, so I will keep this rather brief today, but I will focus on some aspects of groundwater and the drinking water supply, which is probably the most important part here, that we have clean, healthy drinking water. And geothermal water is, of course, also related topic. But we spoke about geothermal water already yesterday as an energy resource, so I keep this brief today. You probably know about the water cycle, which is commonly discussed, that there is precipitation from rain or snow, and this water falls then down on the ground, and part of it is just running off in streams and rivers down to the sea, but part of it is also infiltrating the ground and becomes then finally groundwater. But also this groundwater can be discharged again in springs, both natural springs or artificials that we would usually call also wells. So, and then we have, of course, evaporation and transpiration to get the water back into the atmosphere. Keeping this very brief. The geologists are mainly involved, of course, in the part of the water cycle that is the groundwater flow and groundwater discharge. Groundwater, to keep this brief, is the water that is flowing in the ground, where we have a continuous water-filled part that we call the saturated zone. Part above, that is called the vadose zone. There is also some water as a kind of films around the grains, but it cannot really flow. And this is typically not called groundwater for that reason. So, so we call the groundwater that part of the water that is able to flow in the subsurface. There are the beds or the layers where we find the groundwater are referred to as aquifers. And there might be unconfined aquifers. That means that above them is no impermeable layer, no rock that keeps where water cannot flow through. So we find the water builds a so-called water table. And there are also so-called confined aquifers. There are confining beds, so very low permeability layers in between. There the water cannot go through, and the water has come from somewhere, from other places where these beds are exposed, for example, or very slowly these confining beds are also allowing some leak through, of course. There is nothing that is really, really impermeable in nature or at all. So there might be also confined aquifers that have no contact to the water table or to the surface. And there can be also several layers of groundwater on top of each other. Finding the water table is, in fact, a very important topic. If we want to find the groundwater, mainly if you want to have drinking water, of course, we need to find the part, the clean water, the non-salty water that is in the uppermost aquifer, or maybe the second as well. And for that, we need to drill. If we don't have natural springs, we need to drill and find the water table. And there was someone asking a few days ago about how to find the water table from the structural information only. And to that, I can say at least without knowing the geology of the area, it's not possible at all. And even if we know really the geological situation, the geological history, we will not find the water table without further information. So we always need to have some earlier drills where we can have information on the water table. If we have this information, we can extrapolate and use the geological information to make some at least educated guess where we can expect the water table, but without any hydrogeological information. That means that we have existing wells where we have information on the water table, and maybe also have made some pumping tests that they know the possible discharge from this part. We will not be able to find the water well at any place. So there is structural information is useful and will help us, but it will not be sufficient to find the water table at any place. I hope this answers this, and if you have still questions, please feel free to write them in the comments, and I try to answer that later. Okay, I will answer all the questions in the end of this lecture. I will keep on in my slides first. So this has also to do with the structure, and that might be the cause for this kind of misunderstanding that caused the question by the viewer some days ago, that I mentioned the fracture permeability, which is my expertise. My specialty has to do with estimating permeability of fractured rocks when we have information on the fracture systems. For that, we, for example, go to outcrops. Here you see a sandstone near to Göttingen in Germany, which is nicely fractured. We always need to be aware that the fracture system that we will find at depth is never the same than at the surface, but we can still gain useful information from surface outcrops because we can see how the fracturing reacts to the layering of the rocks, for example. In this case, we see a sandstone which has some clay beds in between, and you see very nicely that the fractures, even quite large fractures that have an opening of several centimeters here, are stopping at some of the clay beds. So there's a strong interaction of the stress field in the rock and the fracturing that occurs there. In soft layers, we have lower stresses, and that is why extension fractures, at least, are formed much more difficult than in stronger rocks, in rocks with higher Young's modulus. That is maybe a little bit much now, so I will not go into the details here. I will give some other lectures on the topics of fracture propagation and related fluid flow in the next weeks, sometime again and again. But there are also some older live videos from last year that are still available on Learning Geology page. So if you check for them, if you're interested in this topic, you can watch still these older videos. Some of them are on YouTube already as well. One very important topic is, of course, that we need clean drinking water. And so we need to have no contamination in the drinking water. The general thing is, of course, that we don't want to have any chemicals or some pollutants that flow in rivers, for example, from the industry or something. We don't want to have them to drop and to pollute our drinking water. Hydrogeologists are then also involved in finding or kind of try to estimate how much we need to do to keep this drinking water protected. So how much we could maybe take into account if pollutants, if we cannot avoid it completely, that there are pollutants coming into the ground, but there can be some calculations made how long it would take until the groundwater would be reached. And so also if it's possible to dissolve the pollutants or that they go into a larger area and will not harm the drinking water at the part where we are drilling it or want to exploit it. For that, it is, of course, best if we don't pollute at all. And it's also, in some cases, it's not really possible not to pollute, or there is already a pollutant, and we have to make sure that we don't drink the wrong water, so to speak. So it's better, of course, to try to avoid this, but in some cases, it's necessary that we make some. For example, hydrogeologists often make numerical models because these fluid flow calculations are way too complex to take into account the local geology, to do that analytically, so just with equations. So then rather numerical models are made. Here I would like to show one example about the fracking industry that is a lot discussed. We had this topic a little bit yesterday about that hydraulic fracturing, in this case related to the so-called shale gas. So natural gas from shale, deep shale, and very tight rocks that have a very low permeability and need to be fractured before we can take out the gas. That is briefly called fracking. And there are a lot of concerns that the fracking would lead to contamination of the drinking water. And here is a simplified version of a quite complex illustration made by Fischer and Wapinski about fractures from the Barnett Shale fracturing in the USA. And you see there that there are the fractures here induced by the hydraulic fracturing in drill holes. And they measured the height of these fractures. And there is, of course, some variation. But you see that there is a height that can be up to 1,000 meters. That is very much. But still, the fractures are so deep that they will not meet the groundwater. So the aquifers that have groundwater really that we can use. And so this is a German word for groundwater. So the uppermost part is only the drinking water. So at 500 meters depth, as it's written here, we usually have so much salt in the water that we don't use it for drinking anyway. So this is kind of showing that the fracturing or the fracking process is not really harming the drinking water at all. So there is no risk in that the fracking fractures become so high that they would meet the groundwater layers, so the aquifers, so they would not harm our drinking water. And in fact, this study that showed that there was a study here in Germany some years ago, but this is applicable to other countries as well, that there are, of course, potential risks on the drinking water from fracking, but the fracturing itself doesn't really provide any risk on the drinking water. It's rather that, of course, some chemicals can come from the layers where the fracking is done up to the groundwater beds, the aquifers, but not through the fracture itself, but maybe through the drill hole if there is the cementation is not good enough. And in fact, these authors came to the conclusion that the most dangerous part for the drinking water and for the general public is not the fracturing process itself or what is happening in the subsurface, but if one of the trucks, the lorries that provide the chemicals to the drilling site is as an accident, and these poisonous chemicals are coming out of the truck and contaminate surface water. So this is I'm not in the gas industry, and I'm not paid by them. I was asked that some time ago when I gave a similar talk, but still I'm absolutely convinced that the fracking itself is not really dangerous, in particular not if they are not using any pollutants like in the geothermal industry. They usually use only clean water to do the fracturing. But still also when we have these chemicals added, the dangerous process is not the fracking itself. It might rather be some problems in the surface industry of this place. But of course, you may express your own thoughts of that topic on that topic in the comments if you'd like to. A brief collection of the contribution that geologists make when we are dealing with water. Geologists try to construct also the water table. If we know from several places the water table, then we can use this knowledge to interpolate the water table. For that, it's not only simple geometry, it's also adding, of course, geological information on the local area. They do make estimates on the fluid flow. I already said that is mainly done with numerical modeling, because the real pure analytical modeling cannot take so many complexities into account. Geologists help when it's about to find the drill site for drinking water. We make pump tests and tracer tests. Geologists are able to interpret the geophysical data or the geological data, the hydrogeological data that is available, and to estimate, for example, how much drinking water can be extracted to keep the reservoir sustainable, so not to take out too much at the same time. And they are also involved in planning further drill holes, of course. So this is what I come up with, but if you have further ideas, please add them into the comments. So if you have any questions or comments, just place them below this video in the comment section, and I will now go into answering the comments or the questions that I can see. In case I don't see your comment or question, I will now, because sometimes Facebook does not show all the comments for whatever reason. And this is not only my problem, I know this from others as well, that sometimes they don't see all the comments during a live session, but I will come back later and try to answer your questions there still. So in case you don't have any questions, we will meet again tomorrow if you like. Tomorrow will be the last part of this series, and that I entitled Geology for the Future. And tomorrow the focus will be on volcanoes and earthquakes, because these are the types of natural disasters that are those that where geologists can really contribute, but also a little bit maybe on landslides, for examples, that are of course also a geological topic. Tomorrow we will talk about, or I will talk about, natural disasters. So I will now exit this presentation and check if you have any comments here. I see that there is quite a number of comments. Most say hello. And I check now here if there are any questions. I know also that there is always a delay. So you see that about half a minute later than I see, or I'm talking really. So I need to wait a little bit to give you time. Again, comments where you are watching from. Ildiko from Romania. Kekai from Thailand. Kabir from Nepal. Amagana from Mali. Daniel from the US. Pont Mkse, sorry if I don't pronounce this correctly, from Thailand. Victor, I remember this name. Guten Tag. Hello. Guten Tag is good afternoon, or in German. I would like to know which method do you use to estimate the fracture permeability? Yeah, well, these are a number of methods. This has to do mainly with that we do numerical modeling when we have the number of fractures and the parameters of the fractures, like the height and the opening and so on. And for that, there are programs where we can estimate or calculate the permeability for individual fractures. And if we have then also information on the matrix permeability of the rock, for example, and do some statistics, then we can at least make an estimate of the fracture permeability. So this has always to do with statistics, because from outcrops and drill holes, we have only limited data, of course. We will not know all the fractures in the subsurface. We'll never know them, all of them. But we combine the data that we have from outcrops and drill cores or drill holes and geophysics, for example, and general knowledge of the area and the geology of the area, the rocks that exist there, and make an estimate, which is never the exact permeability, but more than an educated guess, I would say. So an estimate that makes it possible to have at least a range of fracture permeability, that has mainly to do then to find the best place where to drill to during when you are looking for petroleum or geothermal water, also for groundwater, and you don't want to drill in the place there it is rather tight. You rather want to drill in the place where you have a high fracture permeability. And so there are some general things that can be used, like that the damage zone of a fault zone is often a good place, but we also have to take the hydraulics and the local stress field into account. So it's never a very 1, 2, 3 very simple thing, but it is possible to give some advice at least, and to find the best place where to drill to. And this has also to do then with the planning the well path as well. So I hope this helps. If this, you feel free to add, of course. Victor again says, do you estimate permeability by using logs or cores? Well, this is mainly from cores, really. But logs can also give some indication. For example, if we have resistivity logs, and in a layer is a very low resistivity, we can expect that there, and we know that it's the same rock type from other logs. We can guess that there is aquifer there, there must be free water because this lowers the resistivity, for example. It's also that we can, of course, see fractures in image logs, and we can also use the difference between the sonic log and the density, so the gamma log, to find the fracture permeability. That is maybe a topic for a more detailed lecture on this topic. Christina says, may I ask to tell a bit about desalination? So you mean taking salt water from the sea and use it for drinking? Well, this is of course one thing that is one method that is done very much in many countries where there is not enough clean groundwater to be drinking water. But this is mainly a technical thing, really, that you use marine, water from the sea. And I don't think that's really a topic that is involving really geology. And I must admit that I don't know much about these techniques. So I cannot really talk about this. And this is a little bit outside my field. Tor asks, isn't it safe to drink a groundwater? Well, this depends. In some places, groundwater is very good. So this really depends. It's difficult to say it's generally safe or it's generally not safe. I would not drink it if I don't know it. But in most areas that I know, drinking water from a natural spring is definitely possible. And I know in Germany, at least, the drinking water is probably the resource that we use is that has the most tests, and they're checking this all the time. So I always drink tap water, and or almost always, and because this is the cleanest water that exists here, and it's even the restrictions are much more strict than for bottled water. But I know, of course, this is different for other places, and in some areas or regions and countries, it's maybe not the best idea to drink the tap water or spring water. But this depends on the region, and I cannot say this generally, really. Nodas says pollution of aquifers by fracturing activities happens during cementing the well. Probably yes. 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 The fracturing itself. Well, at least not the aquifers that we really use for drinking. If they are much deeper aquifers, really. That can be, of course, meet the fractures, the fracking fractures, the hydraulic fractures, but during in places that are really drinking water, it's probably rather during the cementation, and if mistakes are made and it's not done properly. Abdullah Hill asks, groundwater recharge is another issue for hydrogeology? Yes, of course, yes. Groundwater recharge. How much groundwater is built or rebuilt after when we have rain? And so this is also, thank you for this comment. Hydrogeologists are also able to make some estimates for that. Yo Soy is from Peru watching, he says. Doesn't Yo Soy just mean I am? Well, sorry, but maybe this is a real name. Christina says, so how to measure the water quality? Well, this has to do with the hydrochemistry. So if there are any heavy metals, for example, inside, or if there are any biological things like bacteria or other things that are not healthy. So it's mainly, it's done in the laboratory, and in some places it's also that some what is it in English? Chlorine, I think, is added to the drinking water to kill the bacteria or the microbes that are inside the water. Then I would not recommend it for drinking, but it can still be used for many other things. But I guess that's more or less it. About the water quality, Manuel says, hello from Spain. Hello, Manuel. Fausto says, can you tell us about the importance of aquifers of the permafrost? Oh, permafrost. I know, of course, what that is, but well, I don't think I know very much about the aquifers in permafrost areas. That is a little bit tricky. Well, no, I don't think I can really tell you anything about this. Of course, when the ground is freezing and defreezing every year, this will have some effects also on the local stress field in the aquifers, I would guess, and then the local permeability may also change by that. But sorry, I cannot really tell. This is a little bit outside my field. Luis says, can we clean the contaminated water with geological methods? Well, in a way, yes, we can, of course, have the contaminated water filtered through the rocks. So if we just have a very deep or a very thick layer of rock where the contaminated water is dripping through until it reaches an aquifer, for example, then the geological media, so the rock, will act as a filter, and so the pollutants will be kept in the rock, and the drinking water or the groundwater can be then still used. But this may take quite a while, so it's a question of tens or hundreds of years, I would guess, that this really takes time. Onal asked about disadvantages of overusing groundwater. Yeah, this is also a point, of course, that if we take out too much groundwater, and someone else asked about the recharging of the groundwater. So if we overuse, so if we extract much more, then we can recharge. If there is recharge, then of course the groundwater, or in this case rather the drinking water level is dropping all the time. So and we can use so much. If we overuse too much, then there will not be any groundwater for drinking purposes left, and that can be a very great problem. That's absolutely true. Yes. Thank you for adding this. Fausto says here, in Argentina, we have a few, and it's a national patrimonium called their importance. I'm not absolutely sure what you're referring to, but yes, you mean the permafrost that you asked before. Yes, yes, then you may add to that. I'm afraid I'm not really, we don't have permafrost areas here, and so my knowledge is very basic on that only. So probably your knowledge is much better than mine. Christina, she's replying to Fausto and says, yes, that is the frozen ground. Yeah, that is the ground that is deeply frozen, and in the summertime the surface part is thawing, but it's then freezing again during the winter. But you have a part of the ground that is always frozen. Guido says, if we are talking about a coastal aquifer, how can the advance of the polluting plume of seawater be calculated with geological methods? Yes, well, in general, when you have a coastal aquifer, there's always a kind of, what is that called? One part of drinking water or clean water below, for example, the island, or below the coast rock. But there is always the salt water from the sea that always comes also below the land. And if you take out too much water, then you will get the salt water from the sea into your drill hole. And that can be, of course, a problem if the discharge is too high. So if too much water is extracted, this can be a very difficult situation. And to calculate this, yeah, well, you need to know about the permeability of the area, of the layers in the ground, and you also need to have information on the how much water is extracted from the ground, and then you can make some calculations. And so if you mean not the seawater that is coming into the well, but also other pollutants, then it's done in the same way as for other places. When you have information on the hydraulic gradient and the permeability of the rock and so on, then you can make some calculations, mainly through numerical models, because again, your analytical models are too yeah, I cannot deal with such complex situations. Also, yes, is probably about the permafrost again. And Manuel also says yes, and Abdullah Hill says thank you. Okay, these are the comments that I can see. I think I didn't miss any of those that I could see. So I wait for a second here if there are any more comments or questions coming. If this is not the case, I say goodbye to you, and maybe I see you tomorrow for the last live session of this series that is then on natural disasters. I will look back into the comments and questions later and see if there are other further comments coming. So in case I missed any, I will reply to you later. And if you watch the replay, of course, it's the same. I will come back and try to answer your questions. So I see mainly some thank yous here. I thank you for watching and participating also in the comments. And yes, maybe we see each other tomorrow. Bye-bye. Take care. I like that. No.